All right, what's up, everybody? Here we are with now, I guess, technically the actual last lecture of thermodynamics and statistical physics. So this is just going to be a fairly brief discussion of black body radiation. Black body radiation. All right, so most discussions of black body radiation initially focus on what's so-called the UV catastrophe. If we were in person right now, I would ask if anybody knew what the UV catastrophe is, how to describe it. Since nobody's here, I guess I just have to. So basically, the way this works is that if you think of electromagnetic radiation in a classical sense, it's a continuous object, some field, right? So you can break it up forever and ever. So basically, you've got some kind of waveform, call it some electromagnetic wave, and you can zoom in further and further and further, and you can dissect it continuously. So every single point in here has an infinite number of points in between it. Now, if we consider this waveform in a box, as we always do, we'll take it in a box. Then the way we can think of these waveforms is just corresponding to simple harmonic oscillators. So basically, in order to get some specific waveform, which might not look as nice as this, something that looks like, I don't know, something like this. It could be anything at all as long as it's not folding back on itself. That in order to get some specific electromagnetic radiation waveform, you're generally going to need an infinite number of harmonic oscillators superimposed on each other in order to actually get the correct waveform. But the problem there is that since each of these harmonic oscillators contributes a finite amount of energy, and you need an infinite number of them in order to construct a specific waveform, that classically there's an infinite amount of energy corresponding to the electromagnetic field in a box. So that's a very rough description of what the UV catastrophe is, but it carries the proper ideas. Okay, so basically it can't be correct that radiation or the electromagnetic field is actually continuous. So what is it actually? Well, it's discontinuous. And who comes to our rescue? None other than quantum mechanics to the rescue. So just a little bit of historical background here. Max Planck, who the distribution we're going to derive is named after, in 1900 derived these correct results, the correct results that we're going to describe in just a little bit, by assuming effectively that the electromagnetic radiation only came in discrete packets. And at this point in time, there wasn't actually a good reason for him to think this. It was just a nice calculational tool that he threw in order to get things to work out properly. And so now, obviously, like these packets of electromagnetic radiation, these discrete packets, are called photons. And also, Einstein used this idea that the electromagnetic radiation is discretized into photons to explain the photoelectric effect, which he went on to receive the 1921 Nobel Prize for. So this is pretty important stuff. Okay, so getting back to the main idea here. So quantum mechanics is coming to our rescue. Well, what is quantum mechanics going to do here for us here? Well, let's think about the states of a harmonic oscillator. So quantum mechanically, a harmonic oscillator has discrete energy states, right? So it has energy states that look like the following. So we go, lowest energy state is, we'll just call it 0, but they come in units of h times f. Obviously, you can't actually get to 0 from a harmonic oscillator, but we're going to call it 0 for this time. So if we can consider the quantum mechanical harmonic oscillator, and we calculate the corresponding partition function, well, in that case, the canonical partition function is just C. Obviously, the lowest energy state will just contribute an e to the 0, so that'll be 1 plus e to the minus beta times the energy, h times f, plus e to the minus beta times the energy again, 2hf, and on and on and on. We showed before this looks like the geometric series. So we can write it as the following rather than infinite sum. We can express it in closed form as this. And now we can use the previously derived formula for the average energy corresponding to the canonical partition function. And that's just given by this expression, which we had shown before. And so if we use the partition function we just showed for the harmonic oscillator, then there we go. Okay. So now we just need to realize that energy for the harmonic oscillator, it comes in units of HF. So energy comes in discrete packets of H times F. So therefore we can take the average energy and we can easily arrive at the average occupancy in terms of units of energy just by taking the average energy and dividing by how much a unit of energy is. So if we do that, we just take this expression, divide it by H times F, we can get what we call the average occupation of the number of packets in whatever state we're talking about. And so this is just what we call the Planck distribution. HF all over K times T minus 1. Planck distribution. And so through this derivation and using the quantized energy states of the harmonic oscillator, we see that actually quantum mechanically, this UV catastrophe is avoided. And why is it avoided? Well, it's avoided because of this factor right here. Because if we consider, let's think of this as like, consider shorter and shorter wavelengths, such that the energy of the electromagnetic radiation is increasing. Shorter wavelengths corresponds to higher frequency, right? But it's 1 over an exponential factor. So this term right here exponentially suppresses high frequency or also high energy radiation states. So you still do technically have radiation going all the way up to infinite frequency, but, well, I mean, that's not absolutely true. So stuff starts to break down as you get close to like the Planck scale or something like that. But at least for the moment, you can consider taking F all the way up to infinity. But this term takes care of that because it nicely suppresses everything that gets higher than some specific range. Okay, so effectively you can get this a lot easier just by taking the Bose-Einstein statistics that we had derived before and just saying that particles, the particles that are bosons in that case, are photons, and photons don't have any kind of interaction with each other. And so therefore the chemical potential for that case is 0. So let's just write that could also derive by assuming the photons are bosons with chemical potential 0. And so you can think of the chemical potential as being 0 because photons don't interact with each other, at least in this approximation. Generally, they don't. All right. So we have a distribution that gives us the occupation for specific frequencies. But now we could ask ourselves, what for example, the total energy is that corresponds to the entire distribution that's possible for frequencies. So we'll start to describe this by just considering, as we've done many times, a one-dimensional box. So start with a 1D box. We'll say it has length L. All right, well, the wavelengths that can fit inside of this box are just going to be 2L over N, because the wave has to go to 0 at the endpoints of the box. And we can assign a momentum as hn over 2L, where of course n in both of these expressions is 0, 1, 2, blah, 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 on and on. Okay, so now, this is just using the way we define P, of course, and how we've done it before. It's just by using the de Broglie relation for the wavelength and the momentum, which is being used here. So, okay. So now what we'd like to do is write down what the energy is of the photons. Now, photons are a different class of particle than what we've dealt with in the past. So in the past, we could just say, oh, our particles are traveling fairly slowly, so we don't have to actually consider special relativity. But of course, photons are the objects which set the scale of what special relativity is, right? Because they have to travel at the speed of light because they technically have 0 mass. So an easy way to derive the energy of a photon is to just use the typical relationships that you know from like your E&M class. So we know that the energy is related to Planck's constant times the frequency, so we can write this. And we should know, hopefully, that the frequency is related to the wavelength just by the inverse and then a factor of c. And so we can take this, throw it in there along with what we have our wavelength to be up here, and we can get the following. So epsilon, the energy is hc over lambda, which is equal to hcn all over 2 times L. And as we always do, we start off with a 1D box just because it's easier to work with initially, and now we can easily generalize the statement to a 3-dimensional box. So generalize to 3D box. So obviously the only quantity that can change here is this n. So all we have to do is just change it as follows. So it's just going to be the magnitude of all of these n's. So there's an x direction, there's a y direction, there's a z direction. So we got to take all those different n vectors and produce the corresponding magnitude of n that we see up here. And so generally we're just assume that we're working in 3 dimensions, and we'll write it as just an n. Okay, so this quantity here and this quantity here are technically different because we're considering 3-dimensional space here and 1-dimensional space here. Everywhere in the future, this n will always refer to this quantity, so just don't get confused by that right there. Okay. So we set out to find the average energy. And now we know how to write the energy for a given n value for our oscillator state. So to find the average energy to be, as we do, is a U, capital U. And we will sum over nx, ny, nz, epsilon, times n bar. So there's just the Planck distribution as a function of epsilon. Cool, so it's just the energy times the distribution, and so that will tell us the average energy. All right. I forgot to include something here. Where did it go? This 2 got slipped in here because there's technically 2 unique polarizations corresponding to every single energy state. So that's something we throw in just because we know that. We're not obviously doing this in full gory detail because we don't want to go fully into E&M in order to just discuss the Planck distribution. But so we've got this general expression for the average energy. We can expand it out because we know epsilon, we know n bar, the Planck distribution. So this will just become following, and it'll just collapse all the sums into this one expression, and y and z hcn all over 2L times 1 over e to the hcn all over 2LKT minus 1. All right. Now, again, as we always do, we're just going to assume that there are so many n's that we can approximate this as an integral and evaluate it that way. Okay? So again, we're considering harmonic oscillators, so what we actually have to evaluate is just the octant that corresponds to those n's, because n's can only be positive, right? So now u can just be written as the following, and we're going to evaluate it in spherical coordinates. So we're taking n, x, n, y, and z, those coordinates, into spherical coordinates, where we'll have like a radial coordinate, we'll have an azimuthal coordinate going off of the xy plane, and we'll have an azimuthal coordinate, why am I writing d phi? Phi. And we'll have an azimuthal coordinate phi, that goes around the z-axis. And remember, if we're only integrating the octant, this doesn't have to go around the entire z-axis, right? So that'll be constrained to just go to from 0 to pi over 2. So if we change that discrete sum into an integral, we would get the following. So we'll have an integral from 0 to infinity over dn, this radial coordinate. We'll have an integral from 0 to pi over 2 of the azimuthal coordinate theta. And we'll also have an integral from 0 to pi over 2 for the coordinate phi. And then, of course, the measure changes. So you pick up this factor of n squared sine theta, as you always do for changing to spherical coordinates. And then you just also have hcn over L times 1 over e to the hcn all over 2LKT minus 1. Note that the factor of here, there was a factor of 2 here and a factor of 2 here before. Those should have just canceled out. So yeah, those go away. So you don't have a factor of 2 at this point. All right. So just carrying out this integral, this is just a little bit of grunt work at this point. The angular pieces, they evaluate to pi over 2. So this entire thing turns into an integral from 0 to infinity of dn pi hcn cubed all over 2L times 1 over e to the hcn all over 2LKT minus 1. All right, now to evaluate this, what we can do, well, actually, our intent isn't necessarily to full out evaluate this, but put it into a different form so we can call it something that is commonly used in literature. So this might not make a lot of sense, but just wait and see. So we're going to let epsilon be equal to hcn over 2L. So remember, this is just the energy. So then we can write d epsilon as hc over 2L dn. Therefore, dn equals 2L over hc d epsilon. And of course, you could solve n over here. So n is equal to what? 2L epsilon all over hc. So just taking these expressions, throwing them in there in order to get u into this other coordinate, which is just the energy. So now we can change the integral from 0 to infinity over n, the oscillator state, into an integral over the energy from 0 to infinity again. And we'll have the following terms. So we'll have a 2L all over hc times pi hc all over 2L And so we'll have a cancellation there, 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 and there, times 2L epsilon all over h times c cubed, and then good old Planck distribution just sitting out here, minus 1. All right. So at this point, what we want to do is just simplify this a little bit further. D epsilon. So this is going to be 8L cubed epsilon cubed pi all over h cubed c cubed times 1 over e to the epsilon over kt minus 1. So we get a nice little result here, which is that this L cubed, right, is just the volume. And the volume doesn't depend on the energy. So we can take it and we can divide it through both sides, and we can get that U over V, or the energy density, is equal to the integral of, from 0 to infinity, of d epsilon times the quantity 8 pi epsilon cubed all over hc cubed, and that entire expression just over e to the epsilon over kt minus 1. And this quantity right here in parentheses gets a special name, not the integrated quantity, the quantity in parentheses, the integrand itself. It is called the spectrum. And it's usually denoted as U of epsilon. So the spectrum is the thing that you integrate over the energy in order to get the energy density. Okay? So we can actually plot the spectrum to get an idea of what everything is looking like over here. And to do the plotting, we're just going to use x equals epsilon over kt as our variable that we're plotting over, rather than putting in a bunch of explicit constants. So this will look like something like this. It'll go up, we'll have a hump, and then it'll exponentially decay off forever and ever and ever. So this is x, which is just proportional to epsilon. And up here, we are just plotting the spectrum, which, if in terms of x, looks like x cubed e to the x minus 1. Okay, so we see that the majority, we're plotting the spectrum, which is effectively the energy density that needs to be integrated up. So we can see that looking at this right here, most of the energy density lies in this range, with an exponentially decreasing portion of it lying way out at infinity. So I'm just going to say most of the energy density lies here. And so from this plot, you can see how the ultraviolet catastrophe gets mitigated in this case, because as you go out further and further to infinite energies, they are exponentially suppressed, and because they're suppressed so quickly, it actually converges to give you a finite amount of energy rather than an infinite amount. One thing you could do with this distribution is you could calculate the peak. And how would you do that? Well, you would just take the derivative and set it equal to 0. And since this is never changing, it's never going to have more than one maximum. We can see from the shape of it. Finding the derivative and setting it equal to 0, that extrema will correspond to a maximum. So that'll correspond to this point right here. If we were to calculate that, we would get that this corresponds to x equals 2.82. And saying that epsilon is equal to 2.82 kt is what we call Wien's law, which you might have seen before, more commonly in like an astronomy class. And so basically you can use Wien's law in order to determine temperature if you're given a peak energy or vice versa. So yeah, you can basically, like if you ever took like an astronomy class where you did like spectroscopy or something, you could take a spectrometer, you could point it at an object, and you could look at where the peak energy lies. You could record that value, and then you could put it in here, and then just invert everything for T, and then you could give it an approximate temperature. Okay, so that's pretty neat. Very, very useful relationship. Always good to keep in your back pocket. So I'd recommend just memorizing this. Okay, so that was a little bit of an aside of just looking at the integrand that appears here in this energy density. So now we actually want to integrate this. Well, it turns out that if you want to integrate this, you have to go down a fairly convoluted path of using the so-called Riemann zeta function as well as the gamma function. Just to give you a little outline here, so the Riemann zeta function looks like the following. And this actually comes up all the time in statistical mechanics and other places, so it's not like it's crazy or anything, but we're just not gonna bother ourselves with it at the moment. But it looks like the following. It's just this infinite sum here, where you just keep on going up and up and up and up in the denominator. And the gamma function, I didn't write down in its closed integral form, but the best way to think about it, it's like it's what's called an analytic continuation of the factorial. So if you ever considered, hey, what does the factorial do if I put in, I don't know, like a fractional number? This is going to be your answer to that. Or if I have like imaginary numbers, what then does the factorial do? Look at the gamma function. But yeah, so basically we need to make use of those in order to actually carry out the integral. So instead of going down that long rabbit hole, which you can actually just find in the back of Schroeder's textbook, we'll just present the results here, which are really the only important thing that we care about, which is this. 15 hc cubed. Okay, so it tells us that the energy density of this quote-unquote like photon gas, we can think of it that way, in a box scales with the temperature as T to the fourth. So that's the main important result that we proved here. Well, we didn't necessarily prove it, but we got real close, and then we just cited some results. So we got to this point where we actually determined what the integral looks like, and we said, okay, someone else has done the integral before. Let's just use that, which is fine. So we understand how this photon gas behaves if it's in a box, but what if we actually want to see it? Right? I mean, what if we aren't in the box? What if we didn't get the invite to being inside of the box? Well, what we want to consider now is that we've got this photon box and we poke a hole in it. Boop. So we want to ask the question, if this is a photon gas in here that looks like, gives the result that we just derived, what can we see out here? Okay. So the way we do that, we just poke a hole. We call the area of that hole A. Keep in mind, all this is actually three-dimensional, so this should be coming out of and into the page, but I'm just going to write the two-dimensional cross-section. So let's consider the photons in this box, which make it out of this hole right here in some period of time dt. So I'll draw what I mean by that. So basically, the photons that'll get out are going to be found in some kind of shell like this, where the shell in this direction, so going from here to here, is, what's the best way to do this? So that's like delta t, or c times delta t, sorry. We'll write c dt. So c just takes whatever time distance you're talking about, converts it to a spatial distance, right? So for a small amount of time, this is the spatial distance of photons that we're going to consider that are coming out of this hole. This little section right here, of course, we all know how spherical coordinates work. So this little piece right here is just going to be r d theta. And this distance here is what we call r. And this angle here is going to be what we call theta. Okay, so we want to figure out an expression that details how many photons are emitted in this time interval dt. So let's first write what is the volume corresponding to the interval. And so the volume we're going to write generally as dV. Well, rd theta is going to be part of it. rd theta, that's going to be that bit. This bit's going to be c dt. And then we also have the entire other direction that we can't see because I'm writing or drawing a two-dimensional surface. And that will just contribute in r sine theta dV. So phi is the direction that rotates into and out of the page. So it just contributes the usual term that you would see. Okie dokie. So let's take our expression up here and let's write it as the following. So we can write du, or the differential amount of energy corresponding to some differential volume, is the following. So we can take the energy density, and we can just multiply it by whatever this small volume is, dV, right? So now if we just take dV, as we know it to be from this expression right here, and put it in, we will have u over v times c, just two r's, so there's an r squared, sine theta dt d theta dV. All right. So now what we need to realize is that all of the photons in this volume that we've just calculated are not going to be oriented toward the hole, right? So there might be some headed in that direction. There might be some headed in that direction. So we need to figure out what the probability is that all of the different possibilities here are oriented toward the hole. So we're going to call that the probability of escape. So what is the probability of a photon in the shell escaping? Well, we can write this as the apparent area of the hole. So basically, if you're a photon sitting right here, or maybe it's more telling to look over here. So if you're sitting right here and you're a photon, you see this hole. It obviously doesn't look like it has area A because you're some angle away from it, right? So this is going to count for that. So basically, if you're over here, the effective area is going to be smaller, and so therefore the probability of you escaping is going to be smaller. So it's going to be the apparent area of the hole divided by the total observable area for that photon. So basically, out of all of the area that it can see, this entire sphere right here, how much of that area corresponds to this hole right here? That'll give us the probability that we can get through that hole, right? So we can write the apparent area as just A, the area, times the modulating factor cosine of theta. And so you can see that if we're at theta equals 0, cosine at 0 will be 1, so the apparent area is what we would think, 1. And if we're way over here at cosine for pi over 2, in that case, then cosine is 0. So in that case, there is no area whatsoever. So that makes sense. And then obviously just the total area corresponding to these photons at that point is just going to be the area of a sphere with radius r, so that's 4 pi r squared. Cool. So now we can take this probability as well as what we found the differential energy encapsulated in this volume to be, and we can just multiply them together. So the probability of escaping times whatever this energy is going to give us the energy corresponding to the photons that actually escape from this area right here. So let's do that on the next page. So energy escaping from dV is going to be equal to A cosine theta all over 4 pi r squared times u over v c r squared sine theta d theta d phi dt. All right, and the only thing we can cancel out are the r's. So we can rewrite this as a cosine theta. Oh boy, there are some children just like screaming in the distance. They're scared of thermodynamics. I'm gonna guess nobody can hear that, but if you could, it would be funny. Promise me. All right. So we can express the energy escaping from the differential volume dV. Now we want to find the total energy that escapes. So we just have to integrate up this differential volume over the corresponding relevant volume. So the energy escaping, total, I should have written total energy escaping, it's going to be equal to the integral from 0 to 2 pi d phi. Oh, and I should be careful, total energy escaping in time interval dt. We're not integrating over time just yet. So we've got to integrate over the angular direction, d phi. We've also got to integrate over the angular direction theta, which goes from 0 to pi over 2, d theta. And then we just integrate the expression. So that is a cosine theta all over 4 pi u over v c dt times sine of theta. Did we get it all? Yes, I think we did. All right, so yeah, we can carry out the integral pretty easily. And what we get is that our final result is a over 4 u over v c dt. All right, now let's think about this. So what is power? What is that quantity? Well, it's defined as energy all over whatever our unit of time is. So it's energy per unit time, right? So therefore, if we're considering a power over an area, that is just energy all over whatever our unit time is times area. What we have here, if we divide out the area, right? So if we divide by the area on both sides, is just the total power per unit area, right? So if we divide by A and we divide by dt, then we're dividing by the area and we're dividing by the unit time. So this is giving us the power per unit area. So this, well, let's just take off the pieces that we don't want. So let's write power per unit area is equal to C over 4 times U over V. Fairly simple expression at this point, but then we put in our actual expression for U over V, and we get 2 pi to the 5th all over 15 times kt to the 4th h cubed c squared. This is commonly written as just sigma times t to the fourth. And so this is called the Stefan-Boltzmann constant. And the law that tells you that the power per unit area is equal to the Stefan-Boltzmann constant times t to the fourth is just called Stefan's law or the Stefan-Boltzmann law. So it tells you, again, we had already shown that the temperature depends on, the energy density is dependent on t to the fourth. Now we've shown that we can write the power per unit area, which is something that we can actually measure if we're sitting somewhere away from this object. You can show that the power per unit area is some value. And if you can measure it, then you can find the temperature, as long as you can calculate the Stefan-Boltzmann constant, which is just a constant, so of course you can. So that is our main result. Now we just introduce our notion of what we mean by black body. So basically, a black body is just what we call a completely non-reflecting surface. So it's a completely or perfectly non-reflecting surface. So it doesn't reflect anything, it absorbs everything that hits it. So it absorbs all electromagnetic radiation. And likewise, emits radiation. Exactly like a hole does, like a hole in a box. And the way that Schroeder presents this is actually kind of nice. So he basically says, consider a box that's got some photon gas in it at temperature T, and consider what we call a black body, and it's also at temperature T. So basically, if they're both at temperature T, and there's radiation being emitted out of here, right? There's radiation being emitted. Since a black body is just defined as something that absorbs everything it gets, it has to absorb this radiation, and therefore it increases in temperature. And so this this completely disregards the second law of thermodynamics, because if you have heat flowing from one object to another, but they're at the same temperature, right? So this thing is getting colder and colder and colder, and this thing's getting hotter and hotter and hotter, but that don't make no sense. Heat can't flow that way, right? So the solution to this, obviously, since a black body is completely absorbing, it also has to be completely emitting. And so as it emits this, it's also emitting the exact same radiation that the hole is emitting. So this is kind of the conceptual understanding for why a black body emits radiation exactly like a hole. So now you can just say, oh, if a black body has the definition such that it is completely non-reflecting, absorbs everything that it gets, well, we've already figured out what the physics is of looking at a hole like this. Well, now you can say, oh, if something is like a black body, it's completely non-reflecting and absorbs everything, then I can just treat it like the physics of this hole where I've got some photon gas. And it turns out that to a really, really good approximation, well, maybe not really, really good, but fairly good, lots of things in nature can be treated as black bodies. And just the general way to treat this is that if something is not perfectly reflecting, so let's suppose something is not perfect, which of course nothing is, but staying close. But if it's not reflecting, then the way we can express the power, it's just an easy modification. So it's still sigma, and we were saying power over the area before, so we'll put that there, times this coefficient E, which we'll just call the so-called emissivity. And so the way you can think of this, it's just something that modulates how well this thing absorbs and emits. And so if it's 0, then it is perfectly reflective. If it is 1, then it's a perfect black body, and it is perfectly non-reflective. Perfectly non-reflective. And so yeah, that's how you derive the physics of blackbody radiation. So now, if you want to, you can take these equations, you can look at various things in your life, and you can measure the power output, measure the power per area, and you can actually calculate what the corresponding temperature is. Of course, you'll find that not everything is a perfect black body, but if you do this for the sun, for example, you'll actually get something fairly close. You'll actually get something that is like 5,800 Kelvin right here, which is pretty dang close to what you should expect and what it actually is. So yeah, that's all we're going to say about black bodies. Obviously, there's a lot more to talk about here, but we just don't have the time to go into super detail. But hopefully this gives you a nice overview of black body radiation, how it's derived, and how it works. And yeah, this is officially all. Okay, so I guess yeah, good luck on your exam, and we will, I don't know, maybe not talk again, but we'll talk over email at some point in the future, or you'll at least see your grades. So yeah, all right, have a great weekend, have a great rest of your night, and great luck on the final.